Right. So, welcome everybody. Thank you for coming around. Today, it's my pleasure to introduce you to Tim Lichtenberg. I will review his career in 2000. I will start to review his career, where he did his master thesis in Göttingen in Germany. Actually, about a very interesting theme that was gravitational instabilities in protoplanetary disks. So this person also knows one or two things about disks.
Only going downhill since then.
And then he went to ETH Zurich for 4 years, finished his PhD there with the title Thermal Evolution of Forming Planets, Isotope Enrichment, Differentiation, Volatile Retention. So very similar to what he will talk about today. After his time in Zurich, he went to Oxford for 4 years, as I understand, two successive postdoc positions at the Atmospheric, Oceanic, and Planetary Physics Institute. And since 1.5 years, he has now reached his destination in Groningen, in the Netherlands, with a tenure track position. And the title of his project there is Molten Exoplanets as a Window into Earliest Earth. So we will hear more about all these things very soon. Just wanted to mention that he's also very known for as being one of the LIFE supporters. What kind of LIFE? The space mission LIFE, so the Space Interferometer, which might become a potential L5 mission, hopefully at some point. We all hope this is going to happen. And he is also presenting actually about the live stuff tomorrow. Our first speaker in tomorrow's WESN meeting, so the meeting where Vienna and Graz speaker come together. And there he will talk about life, but not today. Today is exoplanet, internal fractionation of atmospheric volatiles on magma ocean exoplanets.
Thank you so much, Peter. Thank you all for giving me the chance to present the research of me and my collaborators here. As Peter introduced, I will talk about these things today and not actually about the live space mission, which is also important, but it's a more future topic. Yeah. So I always like to start with something different a little bit, and in order to, after lunch, to get you a little bit into like a more active listening mode, I have a question for you, or more statement actually. So it's pretty straightforward, one may think. Side of the water ice line in the dry part of the solar protoplanetary disk. I think this is potentially a pretty uncontroversial statement, but I want to see actually what you think about this. So who, if I make you sign up to something, who would sign this statement? And don't worry, I will not pick anyone out to explain their position. I just want to test the waters a little bit and also to raise your hand. So who would sign up to this? Can you please raise your hand just to see a little bit the numbers here? Okay, so maybe half, two-thirds, a bit more than two-thirds. Actually, I would say maybe 75%. Okay, thank you, everyone. Okay, great. Obviously, now I'm going to tell you why I don't think this is the case, rather than supporting that statement. So instead of saying this is true, I'll just as an introduction to here, this is about the Earth, not about exoplanets, but I will try to tell you why the statement is fundamentally important for how we interpret the exoplanet samples. So there's actually very strong increasing evidence that the Earth did not accrete inside the water ice line, but outside of it. Outside of the water ice line, where water ice was stable in condensate form. And this here is just the latest iteration of this, and so I'll shortly walk you through this diagram. If this statement is true, it has enormous implications for what exoplanets are, how they form, and what we can expect about their atmospheric volatile content. So this plot here shows the oxidation state, and I'll go later on in what this means, of a reconstruction of the composition of the planetesimals and parent bodies that are the original bodies that make up the meteorite census. So when this says here, for example, ungrouped pragmatic NC irons, that means these are iron meteorites that formed in the so-called non-carbonaceous group, which is the inner solar system isotopic family of meteorites. And the x-axis here means, you can think of it now for the time being here for now, as the primordial water content of these bodies. So how much water ice did they accrete in the first place before they differentiated, meaning they formed an iron core, a silicate mantle, similar a little bit like the structure of the Earth today, but for these for the parent bodies, the asteroids, they are the sort of precursor bodies of the meteorites that we see today. What is notable here is that essentially all meteorites we know of, with a few exceptions, two exceptions in meteorite classes and the calcium and aluminum-rich inclusions, they all overlap within the uncertainties of their measurements with the Earth, and they all overlap with these blue bodies here, the carbonaceous chondrite bodies, which we know for sure are created outside of the water ice. And what this means is that all meteorite bodies we know of, aside from two, are created outside of the water ice. And if this is true, and you won't believe me, obviously now, then this means that exoplanet populations are completely different than what they are interpreted at the moment. It has substantial implications for example, the radius valley, the origin of sub-Neptunes versus super-Earths, the phase state of the super-Earth population, and ultimately the origin and total budget of atmospheric volatiles in them. There's not only evidence from the solar system for this, because JWST now delivers as evidence that inner disks are water-rich. This is from a paper from last year, Perotti, showing very clear evidence for water features in the inner disk of the PDS-70 disk, inside of this, for example, this proto-planet, proto-giant planet, sort of a very young Jupiter-like planet. And what this means is, and this is from here, this inner part of the disk, actually, what this means is that there's also observational evidence that inner disks, even inside of giant planets, are water-rich, and that planets in there have access during nearly the entire accretion phase to water. And that really shifts around the debate on the origin of volatiles on the Earth, on the terrestrial exoplanets. Because I will actually now move on and explain for the rest of the time how this connects with the exoplanet census and why this changes our view of exoplanets and what exoplanets can be potentially. Does anyone have questions about this? Any burning questions? Good. Yes.
Does that somehow link inside whatever with the carbon richness of?
Oh, we don't know. Well, yes, absolutely. It is. We see these carbon-rich disks as well, which we need to bring in line somewhat with the carbon poorness of the Earth to some extent, the carbon depletion pattern. Generally, there's a volatile element depletion pattern in the Earth, and I don't think we understand. I mean, we don't understand the origin of this. And you often see in the literature sort of the standard canonical theory, but these observations and newer measurement of meteorite classes, they really tell us that's not true. Like the Earth did not accrete, there wasn't a snow line, and the Earth accreted inside, and the giant planets accreted outside. It can't be. This cannot explain both the measurements from meteorites and the disk observations, and also the exoplanets observations that we made. So, in the storyline. Okay. So here was a little shocker to start with. Let's go now into my actual talk. So the main point I want to make in this talk is that all rocky planets, so planets and exoplanets, they are born from magma. They're born hot because they accrete and the gravitational potential energy release melts planets. In the case of the solar system, also the decay of short-lived radioactive isotopes melted the planets, which is an important contributor to this. But all exoplanets form hot just by release of gravitational potential energy. And so this is what you see here is a little timeline of the internal evolution of rocky planets, motivated largely by the Earth, because that's what we have access to. But most of these processes that I mentioned here, and I will not go fully into them, are generalizable at least, and we know are first order important for the structure of terrestrial planets and where atmospheric volatiles go during early planetary and longer term planetary evolution. So this chart starts at the planetesimal stage, which happens at about 10 to the 6 years, goes over to what we call in the solar system the giant impact phase, of which the moon, for example, was an outcome. Then the planet crystallizes, so it was liquid and vaporized before, and then it solidified. And then it goes over in a billion-year-long secular geodynamic evolution, where the mode of interaction between the interior and the atmosphere are strongly different. What I really want to take you away from this plot is not all these complicated words, but the color. And most of this diagram is actually red. And this indicates the phase state of the mantle, which is molten. And as I will spend the rest of my time on, this change in phase state is not just a minor coincidence, but it fundamentally changes how atmospheric volatiles interact with planetary interiors. This is especially important for exoplanets because of the observational biases in the exoplanet measurement techniques that we use at the moment, the transit and radial velocity measurements. We are primed to see short period exoplanets. And these exoplanets are hot, very hot. They're so hot that they are molten actually, at least many of them. And this is illustrated for the small low mass exoplanets that we know of here on the right-hand side. This is planetary radius and Earth radii. In the bottom, you see planetary mass and Earth masses. The dots are exoplanets that we know best, that have the smallest uncertainties and mass radius measurements, and they're color-coded with the equilibrium temperature. And the equilibrium temperature is sort of derived from, so this is actually day-side irradiation translated to equilibrium temperature under a certain assumption about the albedo. But what I want you to take away here also is that all these dots, which are close to the green line is sort of the Earth extrapolated to higher masses. So if you would extrapolate the Earth to higher masses, then you would follow this green line. All those dots that are close to this green line are sort of purple or reddish. And what this means is that these exoplanets, even if they have no atmosphere at all, they would melt because these temperatures are higher than the melting temperature of ordinary rocks on the Earth. And that means that all the exoplanets in the TRAPPIST system are molten. And that means that we cannot use the theories that we have from Earth, from present-day Earth, for the interaction between atmospheric volatiles and the interiors of planets. One of the things why that is the case is that, well, what this changes is that during accretion, the elemental budget that is accreted onto a planet interacts differently with different parts and different reservoirs of terrestrial planets. So the accreted elemental composition is unlike the atmospheric composition. That is very clear on the Earth. The bulk composition of the Earth is very different to what we have access to at the surface and in the atmosphere. So there are various ways how this can happen. So for example, if you have a small embryo that will collide with a planet during accretion, it will somehow interact with this. In most cases, it will create melting. And in this case, there's what this particular here shows an iron core that is inside such a planetesimal and will react chemically with the magma. So there's an exchange between elements during accretion already and also later on between different chemical phases in the planet. This changes what we call the redox or oxidation state. This is my very simplified version of what this means, but it's a fundamental concept for what I will try to explain in the rest of the slides. So you can think of oxidation state or redox state as a sort of planet scale electronegativity. Think of all the elements that the planet is made of, integrate them, and then you can, the elements that make up the planet, sort of set where the total planet sits in terms of electronegativity. If it's more to the right, then we call these planets oxidizing. If it's more to the left, we call them more reducing. You can also think simplified of the abundance of oxygen in those planets, but this is actually too simplifying. It's more the valence, the abundance of valence electrons in the chemical compounds in that system. And what we have then for a given planet at the surface of this planet, not necessarily the bulk integrated abundance, but the surface or where the interaction between interior and the atmosphere happens, this sets the climate of planets. So this is illustrated here on the right-hand side. So on the very important for this talk, gases that are released in this particular simulation for a volcano at 1 bar atmospheric pressure and 1,400 K venting temperature, which is roughly the melting point of rocks on the Earth, which is what the conditions of Earth at present day. And so, depending where you are on this plot, irrespective of what your bulk integrated abundance in the planet, what is at the surface, where this venting, where this degassing happens, the gases that are released are different. So if you are oxidized, like the present day Earth, then you sit somewhere here, and the gases that are released to the atmosphere are rich in water, CO2, and SO2. But if you are more reduced, you sit somewhere here. And so reduced planets that are reduced at the surface in the upper mantles will release hydrogen and CO-rich gases that create a very different climate state from the planets from the Earth, for example. And this has substantial implications for the climate state on exoplanets, because these different scenarios predict very different climate states. Because we have so little knowledge, actually, about the thermodynamic regimes and climates of exoplanets, we need to cover much larger parameter space than on Earth. And so this left-hand plot here shows you for very idealized scenarios the heat flux that can escape to space, to certain types of atmospheres, versus their surface temperature. So this here, for example, this blue line is many of you have heard about this, of course, the steam atmosphere assumption. This assumes essentially that the entire atmosphere is made of steam. And this means, for example, that a planet with a surface temperature of about 500 K would emit about this amount of flux here. If you go to the left and it gets hotter, the planet at some point starts to radiate like a black body, but here in this interval, it would always emit the same flux. And this flattening of this line here is what we call the runaway greenhouse transition, or the Simpson-Nakajima limit. Doesn't ultimately matter. But what is important here is the different volatiles have very different properties, greenhouse properties. And that means that if planets are oxidized like the Earth, and their atmospheric volatile budget is not dominated like water, it means they will cool and evolve differently, very strongly. Not just a little bit, but by orders of magnitude. This is the foundation of what we use to define the so-called habitable zone. So this line I just showed you, this flattening here of this line, defines the inner edge of the habitable zone and makes the assumption that all planets have water inventory and are oxidized. Otherwise, this line does not translate to anything physical. So understanding these different greenhouse and climate forcings in exoplanets is of fundamental importance to understand what types of surfaces we can expect for these exoplanets or how they differ in their climates from the planets that we know in the solar system. So one of the things where this hits very close to home, this what I just told you, is the transition between Venus and the Earth, for example. One of the most important or favorite theories for the divergence between Venus and Earth is that exactly Venus and Earth both underwent through that stage that I'm currently describing. They started hot, they evolved to what they were in a magma ocean state, right? But then something happened. And this something in this theory is the flux, the distance to the host star. So this here is a plot from my model, 2013. And what it shows essentially is the solidification time on the y-axis versus the orbital distance of an Earth-like planet with different volatile emitters. In this case, this is pure water. This is only for steam, only for water, the line that I showed you. And what you see here is that outside, let's say at 1.5, or let's be simple, let's at 1 AU, the solidification time for an Earth-like planet with one Earth ocean, so only the surface water on the Earth, would be about a few million years. Maybe here it's about 3 million years or so. But if you're a little bit further inside, the total amount it takes for the planet to solidify, become Earth-like solid, can reach up to giga-years. Why is that? Because the planet is in the steam runaway case and it cannot emit more energy to the space than it receives from the star. So it actually always heats up and it cannot cool down. It cannot cool down until all the greenhouse inventory is exhausted by atmospheric escape. And only then it can crystallize. And in that particular theory, sort of this suggests that outside of this radius, planets can solidify and end up being water-rich after accretion. And inside of the particular transition radius, they end up desiccated. They end up dry. And in this scenario, this explains the divergence between Venus and Earth, while Venus today has only CO2 left and no water, but Earth actually formed water oceans. So you may ask, of course, is this testable? Is this relevant for us? And potentially it is, because these different climate states have very different, they look different, right? These hot planets and these magma ocean atmosphere states, they are actually quite inflated. This is, for example, a paper that calculated this a few years. This shows the radius change as a function of total water content in this magma ocean atmosphere state, this runaway greenhouse state, as a function of the total water content. And you see this goes up the more water you have, the more inflated your planets are. And so what the natural question then is, how many planets would we need to look at in the exoplanet census to test these theoretical ideas that I'm just talking about? And so we did this. This is actually wrong. This is a paper from this year. So we did this in a paper led by Martin Schlecker from the University of Arizona, Tucson. So this y-axis here shows the scale planetary radius of a given planet as a function of time. And so there are different scenarios here. What is important is that in the Earth-like case, we would expect if every planet starts out and is immediately solidified and everything is fine, there's water, then we expect them to be roughly the same radius always. If they start out like hot, like I just suggested, then they just they remain in this runaway greenhouse stage until they exhaust all their atmospheric greenhouse inventory, like in this suggested scenario of Venus, then it would look something like this. So you start very, very inflated, and then until you lose all your water, and then you would converge toward this line. So Martin developed, used the bioverse framework, which is a statistical. What it does is essentially it introduces a Bayesian way of computing evidence for a particular scenario. So you would populate a simulated universe with different types of scenarios, and then you ask the question, how many planets under which side, which kind of uncertainties do we need to observe in order to test this scenario? And so this is how this test looks like. We particularly focused on the Plato mission, of course, which is also which this institute here is very, very strongly involved. So we looked at if Plato specifically could test this divergence between Venus and Earth idea within the anticipated census that we will get from exoplanets from the Plato survey. So what is the specific hypothesis here? The hypothesis is that we have this threshold installation, specific orbital space, which changes depending on stellar type. And inside of this radius, we expect these planets, if they have any type of water, that they are larger than their counterparts on the outside. So for a given fraction of water and for a given lifetime of this phase, we injected planets that are larger inside, but the same size outside. And then we ran like these simulated surveys with Plato, with a simulated Plato mission on this, and tried to recover the threshold installation for which we expect this transition to happen between inflated and non-inflated planets. This is how one of those runs look like. This is net installation versus planetary radius. This is what we call in this thing an optimistic survey. I think it's actually more like a realistic survey. This assumes that Plato will find 500 planets across the threshold installation inside and outside. It is critically important. And in this particular case, it is very straightforward to recover this jump in mean planet radii. So what we did there was sort of we asked the question, what is the impact of the sample size on this? And for that, we basically, this shows you here what we call the dilution factor. It means the factor of planets that actually are in a runaway greenhouse at the time of observation. Because we don't know that, that's something we want to test for. And so, 100 means that none of the planets actually is in a runaway stage, and 0 means 100% of them are inside of this threshold. And when this line here crosses this gray line, this is what we would observe as what we call as a detection. So we can do that. Bayesian evidence of 3 is roughly 2 sigma, frequentists speak. And so what you see is that about 100 planets at this given installation are enough. So we think, which is a reasonable expectation from planet formation scenarios, so we think that above 100 planets, Plato will be able to test the habitable zone concept. What is especially important here is that actually for the Plato mission, it will be important to have a sufficient sample of M dwarfs in the tested stars, in the observed stars, because the runaway and Plato needs much fewer planets if the sample of stars includes more M dwarf stars. So what we do in this paper is we advocate that the Plato survey should include a sufficient sample size of M dwarf planets, which at this point is not a given. Yeah. Are there any questions about this? Because I will continue to the next topic. Sure there are. So I start from, I don't know.
How many M4 stars do you need? 100?
Well, it is, I mean, I cannot answer that question. It depends on what you call evidence and what is the dilution factor. So how many planets are actually there in this data?
You need transiting planets.
Yeah. I mean, Plato is a transit missions. Yeah.
Which
Exactly.
means, because you have basically say 10% chance that there's a transiting, and then
Yeah.
okay.
I mean, Plato does transiting planets, right?
Yeah.
So in principle, the more M dwarfs, the better. But obviously, Plato actually aims to find transiting G dwarfs. So there's a trade-off there. Yeah. Yes, please.
So these samples, this 100 or 200, is for Earth-like planet, right?
No, no. It's anything. So it needs just to find 100, 200 planets across the installation. Yeah. Yeah. It's
An invasion as like simulation. You also simulate hot Jupiter, and
we
don't
do the analysis. You're right. It goes until I think 3 Earth size or some Earth radii or something like this. So we do a full the catalog for this comes from Kepler statistics, and it includes everything like hot Jupiters and everything. But we specifically focus on things that are sort of rocky. I think 10 Earth masses is relevant for us here, and for those we make this test. So you're right. Yeah, it is anything that is below what is 10 Earth masses in radius 2.5.
5,
Yeah, something like that. This is what this includes. Yes.
good. And compared to the number of stars that Plato will observe statistically, would you expect this to happen?
And so this means let's turn it around. If Plato doesn't find evidence for this inflation effect, then I mean this can have multiple reasons. Obviously, it can be either all the many planets form dry, they lose everything by atmospheric escape, or our theory is wrong. Yeah. Okay, let's move actually to something more planet specific, not population based. So we have this radius valley discussion, which is under density in samples, so less planets between the super Earth and sub-Neptune clusters. And you can see this already on this plot. The radius valley is kind of here in Mars radius space. Here in between, there are fewer planets, and this is the radius valley. So there's if you sum them all up, then there are more planets here, sub-Neptunes, and here, super Earth. And in between, there's a little bit of a dearth of planets. For example, 55 Cancri is one of them, K2131b, HD3167b, and TOI561b. So there's a discussion about why do these planets sit in there? Are they just transitioning? What's wrong with them? Are they weird? I wanna come back to this magma ocean consideration. In particular, I want to point out that in magma ocean phases, the different layers of a planet interact much more strongly with each other than we know from the Earth. So on the Earth, you would expect there's something like this, a segregated core, some mantle, and some atmosphere on top. But a magma ocean is like a boiling pot. So the convection in there is highly turbulent, which leads to vigorous mixing between different chemical phases. For example, there is this metal stuff, this grayish dark stuff here. This is supposed to illustrate iron droplets and trained metals that would form the core on terrestrial planets. And in magma ocean stages, actually, the mixing is so strong that it can prevent the segregation of different reservoirs. Just to illustrate the point to you, this is a simulation, one of the best fluid dynamic simulations we can do of such a system. So this is in general just Rayleigh-Bénard convection. Just to set you up, at the bottom here, this is the metal core. The atmosphere would sit on top, and this is the mantle. And the background temperature is the temperature difference between the top and bottom. So it's hot at the bottom and cold at the top. And then the black stuff in there, these are sort of tracer particles that sit in the flow and they're convected through the flow. And this is a very strong convection simulation. It's 10 orders of magnitude, of actually more. It's like 18 orders of magnitude below the actual magma ocean, but it's the best we can do computationally. And let's look what happens. So in these large eddies, the tracer particles, they actually don't rain out. They should rain out because they are more denser than the ambient flow, but instead they actually accumulate in the eddy. And that means that the kinetic stresses in the magma flow can overcome gravitational settling. And for a super Earth exoplanet or a sub-Neptune exoplanet in such a state, this means that the different layers, which we typically expect to gravitationally segregate, do not necessarily segregate as efficiently as they do on a planet in later evolutionary stages. That means the atmosphere and the mantle mix, and the mantle and the core mix strongly. And this redistributes the elements and messes up the oxidation state at the surface of the planet. So the oxidation state of the Earth is relatively different from the one that we know what presently are. We can not do this really computationally, but we can do scaling analysis of this problem. And this is showing this a little bit. So this computes from scaling theory that we know from convection cell experiments on the Earth. So people have done this in geophysics laboratories with water, actually, and tracer particles, simulate Rayleigh numbers appropriate for these types of systems, at least as far as we can get to. We cannot get to the Rayleigh numbers of these systems, of course, but we can do as best as we can. And then what you can do is you can try to understand the droplet sizes for metal particles, for example, that would be trained on those things, versus the critical size that is required for rain. What you see is that the sizes that are expected from the competition of shear stresses and sort of the tendency of these droplets to grow in the magma flow, versus the sizes that can actually be entrained by kinetic stresses that are carried with the turbulent, the eddies. There's a crossover somewhere at a bit the size of terrestrial planets. So terrestrial planets on the size of the Earth are expected that these droplets rain out and form a core. With super Earth actually and sub-Neptunes, these lines cross, and the sizes that can be entrained and they cross with the expected sizes. And this means that in these planets, you can expect more of a diffuse internal structure between the magma ocean and the mantle and the core of those planets. And just to translate, because that's what everyone is interested, of course, into atmospheric abundances, this means that we can expect reduced compositions in atmospheres. Volcanoes on super Earth and sub-Neptunes can release more reducing gases than we are used to in the solar system.
Why is the turbulence changing in your last plot or also here is it the mass, or is it the scale of the thickness of the
thickness? Yeah.
Yeah.
The Rayleigh number.
Or is it the driving temperature gradient maybe?
It's actually the thickness mostly.
Okay.
So the Rayleigh number is this, and the length of the convecting system is cubic, goes in with a cubic power. So that's the controlling factor. So the larger the planets get, it's a very strong depends on the size of the planet.
So that's your driving scale, then, right?
Yeah, exactly. Sorry, that's yes. Yeah.
You consider magnetic field and dynamo action.
No, but this would I was expecting sort of this question. But what it would do is it would strongly enhance the magnetic field. These types of planets should have a massive magnetic field because these particles are entrained in the flow and are very rapidly cycling through the mantle. Yeah. There's a paper actually calculating this by Leslie Rogers 2 years ago. Yeah.
Is the system rotating as well?
What do you mean? Like in this?
You only have two planes,
Yeah.
basically heating up, cooling
So
down.
rotation would enhance this
Will
conclusion.
you also consider Coriolis?
Rotation, no, I don't. But rotation would enhance this conclusion further because rotation would even add an outward driving force, sort of like that keeps the particles entrained and reduces them. Actually, this is one of the main theories currently for the origin of the moon. That in addition to this magma ocean, the rotation rate of the post-impact system was extremely high, and that this was so high that the different phases of the planet could not gravitationally segregate for a while, which can explain the number of geochemical measurements we have on the Earth. So no, it's not considered, but it would only further enhance the conclusions of this. Yeah, please.
About your simulation. So you said it's you have tracer particles in there.
I know I don't. I just did the analytical
But
calculations.
The simulation
Yeah.
has included tracer particles.
This one's,
In my
yeah.
mind, this would be Lagrangian particles.
Yeah.
So now my question is, in how far is frictional coupling here? Are they completely frictional? Because I'm wondering, nothing is really dropping out of that simulation.
No, it's not true actually. If you run it long enough, stuff starts dropping out.
So is it dropping out or is it moving with flow? This is actually my question. So is it really relatively, has it a different velocity relative to the hydrodynamic flow speed?
It does,
Oh, no.
yes, it
Okay.
does. It does. Yeah. I think it's both happens, but I think it literally gravitationally segregates. Yes, so it settles out from the flow. It's not only that it touches sort of the boundary. Absolutely not. No.
It's a question between frictional coupled or not.
Yes.
So you say it's not necessary.
Yes, exactly. I think I honestly can't answer your question fully. I don't know. I need to check the paper again, what exactly they did. I don't see.
Save more question to the end, maybe.
Okay, I'll follow up a little bit. I think we're actually good. So so this is great. So we have this stuff. So we talked about these iron particles, but actually the same happens for volatiles. Volatiles also strongly interact with the magma. And we have on Earth static experiments that can tell us how much volatiles interact with magma. They basically create a synthetic sample, they put in a certain amount of volatiles in it, they heat it, and then they quench it, and then they measure how much of the volatiles sit in the quenched sample, which is taken representative of the magma when it's at its melted point. And these experiments show that if you have a magma gas system, then specific volatiles very strongly couple with the magma, meaning they chemically bind with the magma. So this shows here gas phase pressure. So this is only one axis. There are multiple axes of this, but I focus here on the gas phase pressure. So this is, imagine the surface pressure of a magma ocean atmosphere system. And this is the volatile solubility that in parts per million weight, which means how much of that magma is water, for example. And what you see is that water is extremely soluble. So in a magma atmosphere system, more than 90 to 99% of the water sits in the magma and not in the gas. This is also the case for nitrogen under specifically conditions, and I'll come to that as during the last 5 minutes. But what I want you to take away from this slide is really that these partition coefficients differ by orders of magnitude, as in this case as a function of pressure, but they also differ as a function of other variables, such as temperature and oxidation state. And this is important because this creates emergent co-evolution of melting in a planet and the atmospheric scale height and budget. If you put more volatiles into the atmosphere, this enhances the greenhouse effect, and this melts the planet, which then reduces again the amount of volatiles in the atmosphere because they partition to the magma and back and forth. So there's an equilibrium state that develops as a function of the coupling between the system. So you cannot calculate just atmospheres or just interiors. You have to calculate both. If for these types of systems, we just do atmospheric simulations, we're not getting the composition right. We don't do interior models, we're not getting the thermodynamic state of the system right. This is doubly problematic for super-Earth exoplanets, because while these planets form and then they crystallize, it may be that their crystallization path locks the majority of these volatiles for eternity in their interiors. So this illustrates this just as a picture, because it's very hard to show this in a few slides. So this is the typical thing that we think happens, so that is usually considered in all our theories for the Earth and for super-Earth. So the assumption is that the planets start molten, and then they crystallize from the bottom up. That pushes the volatiles out into the atmosphere. And that would mean that after the magma oceans crystallize, everything is sort of fine and we can forget about this phase. But from multiple lines of evidence, hydrology, geochemistry, and seismic measurements on the Earth, and on laboratory experiments, actually, we think that these magma oceans crystallize in a manner akin to that. So they crystallize inhomogeneously, either from the middle out, from the top down, or something more complicated. This means that the volatiles that are in the magma at this point get locked in place because they cannot escape through that solid phase anymore. Magmas hold water, solids don't. So they cannot get through here. And that means, if that's true, that if there's any magma phase somewhere down in super Earths and sub-Neptunes, they hold potentially hundreds to thousands of ocean equivalent different types of volatile compounds. So we've calculated what this means for super exoplanets. For example, this paper led by Caroline Dorn 2 to 3 years ago now. And so in this paper, just structural relations, we compared the standard scenario, solid core, solid mantle, just all the volatiles in the atmosphere, with something that includes those considerations. In particular, includes melting and bleeding material. And this shows that if super Earth are indeed molten, we are getting the total volatile budget of these planets severely wrong, because a magma ocean planet that has a sufficient budget of volatiles is actually smaller than a planet, its solid counterpart, because the volatiles will go partition into the mantle, they will sit in the mantle, and we won't see them from atmospheric observations. If we guess the phase state of the planet incorrectly. So if we assume solid planets, but they are molten, we're not getting this coupling correct. And so this means that the interpretation of current exoplanet data that only considers solid planets in the small planet regime does incorrectly account for the different phases in the interior. Second to last case, 55 Cancri E. This is, of course, a planet that is always very strongly observed because it's so bright, the stars are so bright. And the only thing I want to show here is that 55 Cancri, in principle, is a very great test bed for this. Literally a series of 55 Cancri. But what I want to show you here is that JWST actually has the capabilities to test these types of theories for that particular planet. So this is these are mock observations of NIRSPEC and Muriel Varese eclipses made by Anjali Piet last year. So these are different scenarios for 55 Cancri E. This is pressure and bar, this is micrometer, and the different colors here are different assumptions about the rock vapor fraction in its atmosphere. So 100%, for example, means this is a planet completely devoid of any volatiles, and 1% would mean there's a lot of volatiles in the atmosphere. And for that particular observation, you see that we should really be and I think next week, this paper will claim the first detection of an atmosphere on a rocky exoplanet. And this, if it turns out to be true, then it would substantially harden the evidence for this magma atmosphere coupling. And it can hide, because it can hide the volatiles from atmospheric escape, the deep interior of exoplanets. Okay, because I'm running out of time, only the last. So I only talked about water so far, but I want to very shortly also talk about carbon and nitrogen, which are of course important elements for life in the atmosphere. And so I talked about oxidation state and partitioning, and this also becomes important here. So what you see on the x-axis here is again this oxidation state, more oxidized to the right, less oxidized or more reduced to the left. And what you see here is for a magma atmosphere system again, the amount of carbon and nitrogen that sits in the atmosphere as a function of oxidation state. And you see they are anti-correlated. So in a reduced system, carbon sits in the atmosphere, and for an oxidized system, carbon actually sits in the magma option. But for nitrogen, for a reduced system, nitrogen actually goes into the magma and it comes out of the magma in an oxidized system. And this brings us to a very favorite planet of the exoplanet community, K218b, which is a sub-Neptune exoplanet. has been observed and provided the very first evidence for methane in a sub-Neptune exoplanet last year. So you see methane features here, and you see CO2 features here and here. Let's not talk about the DMS thing, but the important aspect of this observation has been that there has been a series of theoretical papers before that observation that predicted exactly this signature, that you have methane and you have CO2. Can be interpreted as a sign of a surface ocean because of a line of theoretical arguments, including partitioning of nitrogen into a water ocean. But I mean, this DMS thing then led to this. But what I want to focus here is that this exact signature is perfectly explained by a magma ocean underneath a hydrogen-rich atmosphere. And the reason for this is that I already told you that nitrogen partitions strongly into a magma. And if we have a sub-Neptune, which is by definition made with an atmosphere of hydrogen, then this is a reduced, strongly reducing system, much stronger reduced than anything we know on Earth. And these are a couple of simulations of a magma ocean planet, sub-Neptune, K218b. This is this oxidation state again. This is the atmospheric nitrogen depletion. You see that if you go to more reduced states, which is realistic for sub-Neptune, all the nitrogen will go and will be sucked up by the magma ocean. And so in this paper led by Olli Schortel last year, we simulated, actually this year, 2 months ago, we simulated the partitioning, the coupling, the photochemistry and the chemistry of the atmosphere, and then compared it to the observed spectrum of this planet. And this magma ocean solution reproduces the spectrum to the same degree of uncertainty as does the water ocean situation. But the important difference here is that it predicts a strongly different CO2 to CO ratio. So here's so zoom in into this part of the spectrum. And so this model produces substantially higher CO abundance in the atmosphere. So this is something you can look and test between the water ocean, the magma ocean scenario for sub-Neptune exoplanets. And I think I'm running out of time. Let me just very shortly say the 2 key points I wanted to make is that the atmospheric composition of exoplanets is strongly linked to the mantle phase state and its redox state / composition. And that most of the CNHS inventory of rocky exoplanets and super-Earths and sub-Neptunes will sit in the interior, not in the atmosphere. And so we need to account for this phase state in order to gain an understanding of the integrated bulk abundance of these volatiles in exoplanets. Thanks so much for your attention.